This presentation reports on a paper submitted to Diagrams 2021, which is about using VisDNA to understand scholarly neural network system diagrams. So I think probably the first thing to talk about is VisDNA itself. So the framework is a visual grammar, and you should see these references. So for example, in this volume, there's a paper, but also VisDNA.com is great for having the latest resources about this. And what we're doing in this paper is presenting a report about applying VisDNA to a specific types of diagram. So when Yuri and Clive have been applying VisDNA, they've been applying it in a sort of quite infographic, data-centric way, but they want it to be able to be used for any kind of diagram, and system diagrams found in scholarly publications are one of those areas that they would hope that it can apply to. And so I've been working to try to do that, and thanks to them for their help in enhancing my understanding of what they're trying to do. So what is VisDNA? VisDNA is a systematic way to describe comprehensively the very broad design space of visualizations and the interrelationships between their constituents. So what we're doing is very much within the scope of what VisDNA is trying to achieve. You can see on the right, there's a table which is taken from their website, which is the latest version, and it explains the different visual encoding principles. So you have different things like whether something is being ordered and so on. So what we're looking at here is not really high specification. We're trying to get quite a high level understanding of the visual encoding principles used. So in Richards and Engelhardt's papers, they are able, because they're quite relatively simple and very consistent in themselves, they're able to go to quite a low level and really specify everything, and to create nice trees for these things. Whereas we're really looking for a bit of a summary level, and I'll show you some of the reasons why we want to do that a little bit later. So neural network system diagrams, we're working on this because this is my PhD thesis, and it's a very large corpus of diagrams that people haven't really been looking at. So I would argue that generally people don't tend to look at scholarly diagrams as a scholarly pursuit in itself, but particularly within computer science, there's not been very much analysis of these happening. So what I want, and particularly within neural network systems, which are a very fast-paced, really evolving field at the moment, and there's lots and lots of diagrams being produced to articulate them. I would argue that the visual encoding choices are extremely varied, and that may well be because the different systems require different kinds of visual encoding. But at the moment, we don't even really understand what people are doing. So I picked up on VisDNA because it allowed a level of specificity that allows me to look only at visual encoding choices, so not worry about what content is included, but really to look quite purely at visual encodings. So yeah, neural network system diagrams are from within a particular corpus. So we're looking at conference proceedings, and they often include these. So they're prevalent, they're heterogeneous, both in terms of the content and in terms of how they're visually encoded. And we have several other papers in this conference which are describing different aspects on this. So be that from a statistical point of view or from within the paper context about citations. So those are two different ones. And there's also a graduate symposium, which I'd be delighted if you're interested in as well. So I've also done interview studies which are about trying to understand how people are using them. So this piece is really about trying to capture the visual encodings used in an unambiguous way in order to compare diagrams, so that we can try to identify some of the practices that are being used. And then further, we would love to be able to establish some good practices, but that's not really within the scope of this work. So here's one example diagram. So this is the only example we'll go through today because it is quite complicated. So, but the level of complexity here is fairly reflective of normal diagrams, or there's no normal diagram, but the average diagram in this space. So thanks to the authors for the use of this diagram. What I've done here is to overlay. You might recognize some of the squares with like BOU or GRP. These are from the Richards-Engelhardt's framework. So I've copied these on and put some leader lines down with some balls on the end so that you can see what we're talking about. And I think it will be worth just going through this a little bit slowly because it might help other people in applying the framework. So we start off with picturing and mapping. So you can see here, picturing is the chess piece is being picked. And so the reason for that is because the chess piece does physically exists and it looks like that. Whereas the chessboard is more of a mapping because it's a 2D projection of a thing. So in the same way, the world does exist and a map is just of the world, but it's a map, it's not according to the Richards-Engelhardt framework. So there's some subtlety here about those things, which I think is useful to understand that there is subtlety and richness in terms of how these things are described. In the blue, so we have grouping by color. So you can see green being used here to group these things together so that you know that they're related in some way, and also the arrows as well. Some of them are green, similarly for blue and purple, and also for yellow with this, but they are simultaneously included by shape and by color. Then, so the encoding by shape down in the bottom, so those are those hexagonal shapes. So that again tells you that these are related in some way. They're using shape in order to do that. For the boundary, so BOU at the top left, so that's almost a document shape with a little folded over corner. That's a boundary being used, and there's boundaries being used throughout this diagram. I've just picked out one example of each so that we can see what is being deployed. For adjacency, this one's a bit subtle. So in so that's the ADG. So where those are written next door to each other, so there's blocks that are next door to each other. They don't have anything indicating that they're related really other than that. So there's not an arrow, there's only the little triangle thing. So because of that, and because it is different to the one that is further away, that is coupling by adjacency. So those are more related together than the one which is further. So that isn't a connecting line per se, but it's a relationship because they are so proximal to each other. The connecting line, so back towards the chessboard, so you've got a connecting line. Yes, there's connecting lines throughout. Some of them are dotted, some of them aren't. But really, we're just looking at whether that feature is, that visual encoding principle is being used. And GRP, grouping by position. So I chose this particular part of the example because there's no arrow connecting these two, but yet you know that they are related because they are positioned closely together in this diagram. And org, so these are, because they are arranged in a sequence, you know that you stepped through them. So in applying Richards-Engelhardt, in applying VisDNA, which originally a couple of years ago I was calling the Richards-Engelhardt framework, we've been learning quite a lot, and there's been some back and forth between myself and Richards and Engelhardt in order to refine this a little bit to make it work in this space as well. So some of the things that we found, some of the things that I think are worthwhile. So emphasis principle. So what I'm going to do now is just flick backwards and forwards between these two slides so that you can see what I'm talking about. So the emphasis principle. So here, there is some emphasis placed by having this central line of chessboards all aligned and disconnected from the other things. So you know that's like the main flow. So I think that in other ways, you can also have like call outs and things like this that are designed to attract your attention. And the Richards-Engelhardt framework at the moment doesn't have anything which captures emphasis per se. So it has sizing to encode information, for example. But if you have like a huge thing saying, hey, watch out, and it's all got jaggedy lines around it, that doesn't have any kind of primacy or any vocabulary for capturing that. And I would like that. I think that's useful because it is a feature of the diagram itself. It's not about the user, which would be out of scope of it, but it's a feature of how things are visually encoded. Contextual factors like assumed knowledge. So again, if we just flick back to this one, so the mathematical notation here means something to somebody that knows about neural networks, but it doesn't mean anything to somebody that doesn't. And so again, it's not really requiring an understanding of the user, but it's the author's intent in terms of, is this designed for somebody that can understand this particular thing? So a more straightforward example would be foreign languages. So if a diagram includes 2 different languages on it, this is clearly doing something different, and it's encoding information in a different way. And so I think there should be, again, vocabulary just to be able to capture that, and it would sit well within the framework. And we've highlighted a number of other small ambiguities which have Richard and Engelhardt very kindly been integrating into the framework slightly, just to provide a bit more precision on some of these things. Again, weren't really thought of in this kind of very complex context. And finally, there's no consistent vocabulary for wrong or internally inconsistent visual encoding. So I'll see if I can show you what I mean here. So, for example, there's 4 circles here, and in the paper, I was not able to establish whether that was genuinely a 4-dimensional object or not. I do not know whether 4 is meaningful here in those 4 circles next to ES. So I don't know if that is, I don't know whether 4 means 4, which means that I don't know whether it is encoding the number 4 in some way. I just don't know. And that makes it not possible to sort of unambiguously or consistently apply the Richards-Engelhardt framework to this. Another example of sort of inconsistency might be within the blue box, you've got these ellipses here, which indicate the continuity, but actually in these smaller ones, you don't have those ellipses. And there's just a bit of like whether or not something is being consistently applied is quite difficult. So at the moment, there's no vocabulary for that they've encoded in one way in this place, and in the same diagram, they've done something different with that same thing. So yeah, it's just very, it's perhaps unusual. So in graphs or in charts, you have really unambiguous encoding. So there exists data, and you can see exactly what that is. But here we've got so much more going on that we don't have that ground truth, and we don't have a way of capturing where multiple different visual encodings are used in some inconsistent way. Yeah. So there's quite a few little bits and pieces that would be useful in order to be able to have a comprehensive description of what's going on here. So a bit more about emphasis. So that could be position or color or uniqueness in some way. So making something really stand out. So in conclusion, VisDNA may be a useful tool for describing consistent visualization practices. So I found some challenges in where it's been inconsistent. And it's a really good idea to talk to Clive or Yuri about this, because it's still, whilst it is like fairly stable, there's still bits around the edges where there's cases that haven't quite been integrated yet, and it can be good to talk to them about it, and they can help as well to provide feedback. So they've been really excellent with me, and I'm sure they would be with you. And I would caution that it's a bit challenging to apply VisDNA where the ground truth is ambiguous. So if you didn't make the diagram, or you don't know what the intent of the author was, it can be a bit challenging. And in those circumstances, I would say an iterated reliability check may be useful. So thanks very much for your attention on this, and look forward to working with you in future.